All right, welcome to another deep dive,
Hmm.
where we, as always, take a listener suggestion and just go deep on it. You know,
Yeah,
that's right, deep dive. And today's topic is, well, it's going to be a little heady, I think, at least for me.
it can be. Yeah.
It's churches type theory.
Yes.
So, we're going to be looking at the Stanford Encyclopedia of Philosophy entry on this topic,
I'm
and
right.
yeah, the listener, had some questions about it. So I figured, well, you're the perfect person to talk to about this.
Well, we'll see how deep we can dive
Yeah.
into the depths of type theory today.
Yeah, exactly. So, just to kind of give everybody an overview, if you're not familiar, and I'm not super familiar with it. I know like the very basics.
Sure.
But the whole idea here is that like everything like has a type,
That's right.
right?
Yeah.
So, like if you're talking about a number, that has a type, or if you're talking about a function,
It does.
right? Like a function that takes something and like spits something out. Um, and it's interesting because like, you can talk about the type of a function. So like you can say, I think they use like, I always get this mixed up. I think it's like open parenthesis alpha beta close parenthesis.
Yeah. So that's one way to denote it. And what that would mean is that you have a function which maps something of type beta to something of type alpha.
Yeah.
And this notation, it's worth noting, it's sort of the reverse of what you might see sometimes. So sometimes you'll see this written beta right arrow alpha, but Church actually used this other notation with the parentheses around it.
Oh, okay.
Yeah.
So it's a little counterintuitive if you're, used to, certain ways of notating things, but that's how Church did it.
Yeah.
Interesting. Um, so that's like, one of the fundamental things. But you can talk about like, okay, well, what about if you have a function that like let's say adds two numbers together,
Right.
right? So you have two inputs and then one output.
Well, the interesting thing here is that building on an idea by Schoenfinkel, Church's type theory represents functions of multiple arguments using functions of one argument.
Oh, okay.
So it's as if instead of one function taking two things at once, you have a function which takes one thing and returns another function which is waiting for the second argument.
I see.
And then only then do you get the output.
I see. Yeah.
Yeah. So it's sort of this nested idea of functions.
Okay, so it's functions all the way down,
Yeah.
sort of.
Yeah, that's right.
Interesting. So they have an example here. So like if you want to talk about the type of the addition of natural numbers,
Right.
right? So you're going to add two natural numbers together. You would write it like this: open parentheses, alpha, tau, delta, dot, 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 gamma, beta, close parentheses.
And I think what's maybe a little hard to get used to with this notation is that it's associated to the left. Yeah. So if we just take a smaller example, alpha, beta, gamma in parentheses, that's not, a function of three arguments.
Yeah.
It's a function from type gamma to a function from type beta to a function of type alpha.
Oh, okay. So it's like you
Yeah.
have to read it from the right to the left.
Yes.
It-
It's sort of like, a function which returns a function which returns a function.
Okay.
And so this is how they were able to handle these multiple arguments in this kind of elegant way.
I see. So you don't actually ever have a function that takes more than one argument.
That's right.
It's just all nested functions.
Yeah.
Interesting. Okay, so one other thing they bring up here, at least in the beginning here, that I think is interesting, is that you can think about sets and properties
Yes.
through this lens.
Right.
So like instead of talking about a set as like a collection of things, you can think about it in terms of a function.
Yeah.
And what kind of function would that be?
Well, they call these characteristic functions.
Okay.
And they would be of type open parenthesis. Ooh, alpha, close parenthesis.
Okay. And what is O?
O is the type for truth values.
I see.
Yeah.
So like true or false.
Exactly. So a characteristic function, it takes an element of type alpha, and it tells you yes or no, true or false, whether that element belongs to the set.
I see.
Yeah.
Okay. So like if I said, the set of all even numbers,
Right.
right? The function would take a number
Yeah,
and tell me if it's even or not.
that's right. Exactly.
Okay. Interesting. And then what about, they mentioned relations too, right?
Yes. So relations, you can think of them as functions as well in this framework, and they would be of type open parenthesis, O, alpha, close parenthesis, beta, close parenthesis.
Okay. And so what is that saying?
So this is saying that it takes Well, again, you have to read it kind of from the right to the left.
Okay.
But you're going to take something of type beta as an argument.
Okay. And it will return a characteristic function,
I see.
which then will take something of type alpha and give you a truth value.
Okay.
So this way you can represent relations between things of type alpha and things of type beta.
Yeah, okay, I see. So it's like a function of functions in a way.
Right, exactly.
Interesting. Okay, and
Yeah.
this all kind of like, I guess, what they're saying is this makes Church's type theory a logic of functions, right?
That's right. And I think this is an interesting point because it kind of puts it in a certain tradition. You know, it's very much in the spirit of Frege's Begriffsschrift, where functions are kind of the primary notion.
Right.
And this is in contrast to something like Principia Mathematica, where the emphasis was on relations as kind of the fundamental building block.
Interesting. So it's like, I guess one of the things this makes me think about is like, what is like the more fundamental concept, right? Like, is it functions or is it relations? Right. And, you know, Church's type theory kind of comes down on the side of functions as being, you know, the more fundamental.
Okay. Interesting. Okay, so that kind of sets the stage in terms of like, you know, the basic idea
Yeah.
of what we're dealing with here. But let's talk a little bit about like the syntax of this. Like how do you actually you know, write out expressions in this language?
Right. Well, before we get into like the specific symbols, I think it's worth mentioning that Church used some terminology, which is a little different from what you might see today.
Okay.
So he used this phrase, well-formed formula, or DROF, of type alpha.
Okay.
But in more standard terminology today, that would just be called a term of type alpha.
I see. Okay.
Yeah. So when he's talking about roughs, he's really just talking about terms. And then when he's talking about formulas specifically, he means roughs of type O, which is that type for truth values.
Okay. Okay. So it's a little bit of a terminological difference there to keep in mind. All right. So then let's talk about the actual like symbols and stuff, right? Like
Okay.
how do you actually build up expressions in this language?
Yeah. So first, he distinguishes between improper symbols and proper symbols.
Okay.
So the improper symbols are just these brackets and this lambda.
Okay.
The lambda symbol. And then you have all your proper symbols.
Yeah.
And among the proper symbols, well, first you have variables.
Okay.
And you need a denumerable list of variables for each type.
Okay.
So you might have, you know, X, Y, Z, and so on of type alpha. And then you have, you know, U, V, W of type beta, and so on.
I see.
And then you have these things called logical constants.
Okay. What are those?
So the logical constants are, well, first you have this symbol for negation.
Okay.
And that has the type OO.
Okay.
So it maps a truth value to a truth value.
Right. Because like not true is false, not false is true, right?
That's right.
Okay. And then what else?
And then you have a symbol for disjunction, which is like an or.
Okay.
And that one, it's a little more complicated, right? The type is double open parenthesis O, close parenthesis O.
Okay.
Yeah.
And then they also have this thing pi, right?
Right. Pi, that's used for the universal quantifier.
Oh, okay.
Yeah. So like for all,
I see.
and that's a type open parenthesis O, open parenthesis O alpha, close parenthesis, close parenthesis.
Okay.
Yeah.
I'm not sure I totally understand what that means, but I guess we'll come back to that maybe.
Sure, we can.
And then there's one more, right?
Right. There's this symbol iuta, which is used either as a description operator or a selection operator.
Okay.
So it has this dual role.
I see. So it's either picking out like a unique thing or
Mhm.
just picking like any old thing.
Right, exactly. And the type is open parenthesis alpha, open parenthesis O, alpha, close parenthesis, close parenthesis.
Okay. All right. So and then the entry says that you can also have non-logical constants or parameters.
That's right. And this is important because, you know, this allows you to talk about specific domains, right?
Okay.
So if you want to talk about, you know, people or numbers or whatever.
You need to introduce some symbols to represent those
Yeah,
things.
exactly. You need to be able to name them.
Okay.
Yeah.
Gotcha. Okay, so that's like our basic set of symbols.
Our alphabet.
Yeah. And then how do we actually like string them together into meaningful expressions?
Well, there's this inductive definition of a well-formed formula,
Okay.
which, again, we can just call it a term.
Okay.
And it's a step-by-step process.
Okay.
So the first step is that any variable or constant of a certain type is itself a rough of that type.
Okay, so like if I have a variable x of type alpha, then that's a rough of type alpha.
Exactly.
All right.
And the second step is if you have a function a of type open parenthesis alpha beta close parenthesis and an argument b of type beta,
Okay.
then applying the function to the argument results in a w of type alpha.
Okay, and how do you write that, like the applying the function to the argument?
So you write that with brackets around it.
Okay.
So you would write open bracket a, b, close bracket.
Okay.
Yeah.
All right, and so then the third step.
So the third step is if you have a variable x of type beta
Okay.
and a WFA of type alpha,
Okay.
then you can use lambda to abstract the variable and create a WF which represents a function of
Yeah.
type open parenthesis alpha beta close parenthesis.
Okay, and how do you write that?
So you write that as open bracket lambda x a close bracket.
Okay.
Yeah.
All right, so it's like basically you're saying, okay, this is the function that takes x
Yeah.
and gives you a.
That's right. Exactly. You're basically defining a property or a mapping.
Okay.
Yeah.
Gotcha. All right, so that's how you build up these expressions. So they have some examples here of like, abbreviations.
Yeah, they do.
So like implication.
Right. So you can write implication using the symbol for negation and the symbol for disjunction.
Oh, okay.
So it's just a shorthand way of writing that out.
Okay.
Yeah.
And they have the universal quantifier also, right?
Right. So the universal quantifier, you can define that using pi and lambda abstraction.
Okay.
And this is quite elegant, actually, because it shows you how lambda is really the only variable binding mechanism that you need in this theory.
Okay.
Yeah.
Interesting. And then there's this other one that I think is kind of interesting. Equality, right?
Yes, equality. So they define equality using this symbol Q. And it's defined in terms of quantification over properties.
I see.
So basically what they're saying is that two things are equal, if and only if they have all the same properties.
Oh, okay.
Yeah. So this is the Leibnizian definition of equality.
Okay. And that, I guess that makes sense, right? Because like if two things are really the same, then they should have all the same properties.
They should.
Okay.
And vice versa.
Yeah.
Yeah. So philosophically, this is very interesting, I think.
Yeah, because it's like, it's not like they're just saying, oh, equality is just this like primitive thing.
Right, exactly. They're actually giving you a definition of it.
Yeah.
In terms of something else.
Yeah, and it's a definition that like, has been debated by philosophers,
for centuries.
For a long time. Yeah. It's this whole idea of like the identity of indiscernibles.
That's right.
And like, whether that's a valid principle or not.
Yeah.
So it's cool that they're able to like formalize that in this system.
Yeah.
Okay, so they have some examples here of like, how to actually use this language to say things. Right.
Yeah. Yeah.
So like one example is Napoleon is charismatic.
Right. Yeah. And they represent this using constants and quantification over properties.
I see. Okay.
So they have this constant for Napoleon.
Okay.
And then they have this constant for the property of being charismatic.
Yeah.
And then they basically say that Napoleon has that property.
Okay. Makes sense.
Mm-hmm.
And then they have another one which is a little bit more complex, right?
Yes. So they say Napoleon has all the properties of a great general.
Okay.
And this one requires a bit more machinery, right? Because you're quantifying over properties.
Okay.
But they're able to express it using pi and lambda.
Okay.
Yeah.
Gotcha. And then they have this kind of, I don't know, like a little story here about
Sheila the ostrich.
Sheila the ostrich, yeah.
Yeah.
And this one is like a little bit less formal, I guess, but it's kind of interesting.
It's a fable.
Yeah.
But it actually illustrates some really powerful ideas.
Okay.
About how you can use type theory to model like states of affairs, plans of action, and constraints on those plans.
Okay, so it's like, Sheila has these pets, right?
She does. A cheetah and a giraffe.
Yeah. And she wants to like move them around.
She does. She's got this this plan to move them between enclosures.
Right. And there are certain like constraints.
Right, exactly. Like, the cheetah can't be in the same enclosure as the giraffe.
Right, exactly. Yeah, so it's like, how do you come up with a plan that satisfies all these constraints?
Right. And the way they formalize this is by defining what constitutes an acceptable plan in terms of these changing locations of Sheila and her pets.
Okay.
Yeah.
So it's kind of like it's almost like a logic puzzle, right?
Yeah, that's right.
In a way.
Yeah,
Okay. Interesting. And then they have a mathematical example too
they do.
with iterates of a function.
Right. So they define what it means to iterate a function.
Yeah.
And they also define the concept of a fixed point.
Okay.
And then they prove a theorem about fixed points. Yeah.
So this kind of shows you that, like, you can do math in this system.
Absolutely.
Right. It's not just
It's not just a logical language, it's also a mathematical language.
Yeah. Okay. And then they get into something which is like really interesting, I think, at least from a philosophical perspective.
Yeah.
Which is Gödel's variant of the ontological argument.
Yes.
Right.
Yep.
So, this is like a classic philosophical argument for the existence of God.
It is. Yeah.
And they actually show how you can formalize that argument in Church's type theory.
They do. And it's interesting because it shows you that you can use Church's type theory as a metalogic.
Oh, okay. What does that mean?
So a metalogic is just a language that you can use to talk about other logical systems.
I see.
Right. So you can use it to study the properties of different logical systems.
I see.
And in this case, they're using it to study a higher order modal logic, which is a logic that deals with necessity and possibility.
Okay. Yeah, I see.
Yeah.
And they have this technique called shallow semantical embedding.
That's right.
And what that means is that you're basically defining the modal operators.
Yeah.
Like, the box, which means necessarily.
Right.
You're defining that within the type theory itself.
Exactly.
Okay.
Yeah.
Gotcha. So it's kind of like you're taking this modal logic and you're translating it into the language of type theory.
That's right. Exactly.
Okay. And they talk about different ways to interpret the quantifiers.
They do.
Right? Like possibilist versus actualist.
Right. And this is really interesting because it shows you that there are different ways to think about what it means for something to exist, right?
Right.
So the possibilist says that something exists if it's possible for it to exist.
Okay.
Whereas the actualist says that something exists only if it actually does exist.
I see. Okay. So it's like, is it enough for something to be possible in order to say that it exists?
Yeah.
Or does it actually have to exist in the real world?
Right.
Okay. That's a big question.
Yeah, that's a big question.
Yeah. Okay. So that's Gödel's ontological argument, which is really interesting.
It is.
And then they have another example here, which is really important, I think, historically.
Yeah.
Which is Russell's paradox.
Right.
Right.
Yeah.
So
Sure.
This is the paradox of the set of all sets that don't contain themselves.
That's right.
Right.
Yeah.
And this paradox, it really caused a lot of problems.
It did. It was a crisis
Yeah.
in the foundations of mathematics.
Yeah, because it's like if you allow that set to exist,
Yeah.
then you get a contradiction.
You do.
Right.
Yeah.
And so Church's type theory is actually a way to avoid that paradox.
It is.
Right.
Yeah.
And how does it do that?
Yeah. So the way it does that is by basically having this type system.
Okay.
And the type system prevents you from forming these kinds of self-referential expressions.
Okay.
Yeah.
So it's like you're not allowed to talk about the set of all sets that don't contain themselves,
That's right.
because
Yeah.
that's just not a well-formed expression in this language.
You're not allowed to have a set which contains itself as a member.
I see. Okay.
Yeah.
So the type system is basically a way to kind of police the language.
That's a good way to put it.
Right.
Yeah.
And to make sure that you don't say anything that's going to lead to a contradiction.
Exactly. It's like a safety net.
Yeah.
Yeah.
Okay. Interesting. Okay. So
Yeah.
So that's kind of like the big picture.
Yeah.
Right. But let's get into the nitty-gritty a little bit more in terms of the axioms and the rules of inference.
Okay. Sure.
So how do you actually prove things
Yeah.
in this system?
Well, like any logical system, you have a set of axioms,
Okay.
and you have a set of rules of inference.
Okay.
And the axioms are just statements that you take to be true without proof.
Okay.
And then the rules of inference allow you to derive new truths from existing truths.
Okay.
Yeah.
So what are some of the axioms and rules of inference in Church's type theory?
Well, they're kind of technical.
Yeah. All right.
But I can mention a few of them.
Okay.
So, one important rule is alpha conversion.
Okay. And what is that?
So alpha conversion just allows you to rename variables.
Okay.
So if you have like a lambda expression,
Okay.
and you want to change the name of the variable that's being bound,
Okay.
you can do that as long as you do it consistently throughout the expression.
Okay. So it's like changing X to Y, but you have to change all the X's to Y's.
That's right. Exactly.
Okay.
And then there's beta conversion, which allows you to simplify function applications.
Okay.
So if you have like a function application, you can replace it with the body of the function,
Okay.
but with the argument substituted in for the parameter.
Okay. I see.
Yeah.
And then there's substitution, right?
Right. Substitution is just, if you have a statement
Okay.
and you have a term,
Okay.
you can substitute the term for the variable,
Okay.
as long as you do it consistently.
Okay.
Yeah.
I gotcha. And then there's modus ponens.
Right. Modus ponens is a very classic rule of inference.
Yeah.
And it just says that if you have a statement, if P, then Q,
Okay.
and you also have P,
Okay.
then you can conclude Q.
Right. Okay.
Yeah.
And then they have this thing called generalization, right?
Right. Generalization allows you to go from a statement about a particular thing to a statement about all things.
Okay.
So if you have a statement that's true for some arbitrary X, you can then conclude that it's true for all X.
Okay. I see. So it's like going from, this apple is red
Yeah.
to all apples are red.
Right, exactly. But there are certain conditions that have to be met in order for a generalization to be valid.
Oh, okay.
Yeah.
And then they have some axioms, they call the axioms of elementary type theory.
That's right.
Right.
Yeah.
And they list them as E1 through E6.
Yeah. And these are just basic logical principles
Right.
that you need to get the system off the ground.
Okay. Gotcha. And then they also have some axioms of extensionality,
They do.
right?
Yeah. Yeah.
And these axioms basically say that if two things are equivalent, then they're the same.
That's right. So, for example, the axiom of Boolean extensionality says that if two truth values are equivalent,
Okay.
then they're the same truth value.
Right.
And the axiom of functional extensionality says that if two functions always produce the same output for the same input, right?
Then they're the same function.
Right. Okay.
Yeah.
So it's like they're saying that the only thing that matters about a function is what it does.
Right. It's not about like how it's defined internally or anything like
Yeah.
that. It's just about, what